Welcome back to Think Cosmos, where we ponder the universe's deepest secrets and wonders. Humanity is at the cusp of a propulsion revolution. While we made it to the moon with chemical rockets and sent probes to the outer planets, our current propulsion tech is simply not fast or efficient enough for deeper exploration of space, especially for crewed missions to Mars or beyond. But that's changing. From nuclear thermal propulsion to plasma engines, solar sails, and even theoretical beam-pellet drives. 2024. 2025 has seen major breakthroughs that are transforming science fiction into engineering reality. These technologies aren't just faster. They're smarter, safer, and more sustainable for long-term space travel. Let's explore the new frontier of space propulsion and what it might mean for our future among the stars. The comeback of nuclear thermal propulsion, NTP. At the heart of this propulsion renaissance is a resurrection of nuclear thermal rockets, a technology originally studied during the Apollo era but never flown in space. In 2024, NASA and the U.S. Defense Advanced Research Projects Agency, DARPA, accelerated development of their joint project, DRACO, the demonstration rocket for agile cislunar operation. The goal? Launch and test a working nuclear thermal rocket engine in space by 2027. And they're making real progress. In late 2024, engineers successfully tested a new nuclear reactor fuel, capable of withstanding the ultra-high temperatures generated inside a rocket powered by fission. This fuel, a HALEU-based ceramic metallic blend, showed resilience during simulated reactor conditions and passed initial heat dissipation and thermal cycling tests. This is critical because nuclear thermal propulsion involves a nuclear reactor heating liquid hydrogen, which is then expelled at high velocity. Twice the efficiency of chemical rockets, specific impulse up to 900 seconds. High thrust, unlike low thrust electric propulsion systems. If successful, DRACO will be the first nuclear rocket tested in space in over 50 years, and the first step toward real-world deployment. Why? It matters for Mars missions. Today's Mars missions rely on chemical rockets, which are powerful but inefficient. A crewed round trip to Mars currently takes about 6 to 9 months each way, depending on planetary alignment and propulsion. That's too long. Why? Because astronauts in deep space are exposed to cosmic rays, polar storms, night, and death. Microgravity-induced health problems. The longer the journey, the greater the risk. Nuclear thermal propulsion could cut the travel time to Mars by nearly half, down to 90 days or less, depending on trajectory. This reduces radiation exposure, makes abort scenarios more feasible, and allows more robust payloads, including crew, habitats, shielding, science equipment, food and water. With NTP, a permanent Mars program becomes more viable, not just a one-time flag and footprints mission. Electric propulsion, VASIMR and ion thrusters. While nuclear offers high thrust for interplanetary transport, electric propulsion offers extreme fuel efficiency, ideal for long-duration missions, orbit changes, and deep space probe. The most promising electric system today, VASIMR, the Variable Specific Impulse Magnetoplasma rocket, developed by Astra Rocket Company. VASIMR uses radio waves to ionize propellant, like argon or xenon. Accelerates the plasma with magnetic fields, has variable settings, high thrust for acceleration, high efficiency for cruising. In early 2025, VASIMR completed a 100-hour endurance test at 100 W, a key milestone for eventual use in cislunar cargo transport or deep space probes. The engine could also serve as a solar-powered tug between Earth orbit and the Moon, refueling gateway stations or pushing Mars cargo ships. Meanwhile, NASA continues to expand the use of ion thrusters on missions like Propulsion to the metal-rich asteroid 16 Psyche, DART, demonstration of planetary defense impact. These systems have already proven their value, and with more powerful versions on the way, they'll soon be steering larger spacecraft farther, faster, sailing with light. Solar sails take flight. 2025 also marks a leap forward for solar sail technology, a propulsion method that uses photons from the sun to gently push a spacecraft. NASA's Advanced Composite Solar Sail System, ACES-3, launching in 2025, will test ultra-thin, high-strength composite booms. Deploy a sail about 80 square meters in size. Prove precise attitude control using sunlight alone. But solar sails are ideal for long-term space missions with no need for fuel, maintaining orbits at unstable Lagrange points. Slow acceleration, but continuous and free. One theoretical application: heliophysics observatories that hover between Earth and the Sun to monitor solar storms with perfect positioning. Eventually, solar sails could be combined with laser arrays, like in Breakthrough Starshot, to push gram-scale probes to nearby stars at 20% the speed of light. The frontier of the fantastic, pellet-beam propulsion and beyond. Among the most futuristic concepts being explored is pellet-beam propulsion, an idea backed by recent NASA NIAC funding. In this concept, a spacecraft in low Earth orbit fires microscopic pellets of material at high velocities using electromagnetic accelerators. These pellets transfer momentum to an interstellar probe, propelling it without onboard fuel. The probe could theoretically reach Proxima Centauri in 50 years. While entirely untested, this approach highlights a new way of thinking. Separate the power source from the spacecraft. Other blue sky ideas in the works include antimatter catalyzed fusion engines, direct fusion drives like the Princeton DFD, beamed energy propulsion, energy propulsion. These systems remain theoretical, but the engineering groundwork is slowly forming. The big picture: opening the solar system. All of these technologies, nuclear, electric, solar, and conceptual, share one goal: to push the boundary of human and robotic exploration. With them, we could reach Mars in under 90 days, orbit the outer planets in less than 3 years, send robotic probes to the Kuiper Belt and Oort cloud, maintain permanent infrastructure at the Moon and Lagrange points, launch precursor missions to Alpha Centauri. It also decentralizes propulsion. Nuclear enables rapid crew transport. Electric powers cargo ships in orbital maneuvering. Solar sails maintain orbits and interplanetary relays. Beamed propulsion may enable interstellar probes. Together they form a toolkit for building a solar civilization. Final thoughts: the rocket revolution has already begun. Space travel isn't stuck. It's evolving. What was once theory is now engineering. What was once confined to white papers is being tested in labs and prepped for launch pads. By 2030, we may have a nuclear rocket in space. By 2040, we may routinely fly astronauts to Mars. And by mid-century, we might see the first human-built object cross into interstellar space at meaningful speed. Every propulsion breakthrough isn't just about going faster. It's about reaching farther, with less risk and more capability. Because to explore the cosmos, we don't just need vision. We need the engines to take us there.